there are 2 trillion galaxies in the observable universe. You need to know that the Milky Way galaxy has got 200 billion stars, and most of those stars now we know have planetary systems. We estimate there are something like 20 billion Earth-like planets, or potentially Earth-like planets, in the Milky Way galaxy alone. So if you're asking questions about what is my place in the universe, you need to know those things. First of all, it's a framework within which you can think. I've been doing some work on black holes, and there's progress being made on that now, which I think is profound and exciting. So they are stars at the end of their life, bigger than the sun, more massive than the sun. So they run out of their fuel, and they start to collapse as gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. And so they collapse, as far as we know, to a point, like essentially an infinitely dense point. But they collapse to such an extent that there's a region around it from which light can't escape. And that's so nothing can escape. And that's a black hole. They're surrounded this region where if you fall in, it's called the event horizon. And if you go across that horizon, then you are going to the centre. There's one way of thinking of that, which is quite cool, which is that the time and space sort of flip from these things. So in the same way that we are going into the future now, so we're going to tomorrow. There's nothing we can do about it. We are going to tomorrow. In the same way, if you fall in across the event horizon of a black hole, you are going into the singularity. So that's your future. Every line points to the centre of the black hole. We have now got photographs of them. So we have 2 photographs, which are radio telescope photographs. One of the one in the centre of our galaxy, which is a little one. It's called Sagittarius A star. So it's about 6 million times the mass of the Sun. And they took a photo of one in the galaxy M87, 55 million light years away. That thing is around 6 billion times the mass of the Sun. So if you took our Sun, which you can fit 1 million Earths inside, and collapsed it down to make a black hole, it would form a black hole when it shrunk. So you squash it down till it's about 2 miles, and then that would form a black hole. 6 billion times the mass of the Sun means you multiply that by 6 billion. So these things, the so-called Schwarzschild radius is larger than our solar system. So what you're seeing there is the emission from the material that's swirling around it. It's called the accretion disk. So you have material that's orbiting very fast, emitting a lot of radiation, and that's what we see. It's a flat disk, by the way. Think Saturn's rings. So this material is very flat. But what you're seeing in that photograph is the light rays being bent around the black hole from that flat disk. So that was a prediction from Einstein's theory, basically. He published it in 1915. And you can predict that that's what one should look like. And then just about, was that 4 years ago now, maybe 5 years ago, for the first time in history we had an image of one, and it looks like the prediction. In science, at the moment, space science, we have this debate a lot actually, because of course space probes like Curiosity that's on Mars, that's really cheap compared to sending people to Mars. And so quite often scientists who want to find out about the world will say, well, we should spend it on robots, we shouldn't spend it on people. I think crewed space exploration is in some ways, I mean, it's clearly true at the moment that humans can do more than robots, so we can explore the place better. It's about living and working off the planet, which I think is quite a persuasive argument, actually. We've already industrialised near-Earth orbit, so it's already a multi-billion-dollar industry. Communication satellites, weather satellites, GPS, whatever. We're already up there. And so learning to live and work in space is, I think, a natural extension of our civilization. Plus the fact, if you talk to Elon or Jeff Bezos, they point out that the amount of resources just slightly above our heads is best. And so I remember I talked to Jeff Bezos actually once. He thinks really simply, and he said, maybe, for example, in the asteroid belt, there's enough metal to build a skyscraper. What is it? It's something like 800 stories tall and cover the Earth if you want. Now, we don't want to do that. But his point was that the energy from the sun is all up there, the resources are up there, So you could almost imagine trying to zone the Earth residentially at some point in the future to protect the planet and do heavy industry off the planet, for example. And it sounds like science fiction, except that now SpaceX and Blue Origin, those people have got reusable rockets. So suddenly the economics become sensible. I think expansion is good, and I think we will expand, and I think we will expand outwards, because there's not much room left on this planet to expand. That's a whole different idea. It's not about gathering scientific information. It's about a frontier and all the benefits that come from operating as a civilization on a frontier, which we've lost on the Earth because there is no frontier left. And so I like that idea. So there is no other planet we can go to other than Mars. You can't go to Jupiter or Saturn, you can't go to Mercury or Venus. So if we want to go somewhere and expand our civilization, it has to be Mars. And everything's there that we need. It's interesting actually, because we know something about the history of Mars, quite a lot about the history of Mars. And it's certainly clear that there was water, almost certainly oceans, rivers. So, and that water is almost certainly still there. So there's certainly ice. There may even be pockets of liquid water below the surface. So couple that with all the minerals and the resources that we know are there, and you have everything you need. So that's the thing about Mars. It's quite nice relative to everywhere else other than the Earth. You can't go to Venus. you just melt. So what is it? 400 and something degrees and 90 atmospheric pressure. So Mars is quite nice. I think there must be, even in the solar system, I would not be surprised if we find microbes on Mars or some of the moons of Jupiter or Saturn where there's liquid water. And the reason is, the reason I think that is a guess, is because if you look at the history of life on Earth, so Earth formed, no life, ball of rock, and almost as soon as it cooled down, we see evidence of life. So certainly 3.8 billion years ago, possibly even further back than that, we see evidence of life on Earth. So somewhere along the line, geochemistry, active geochemistry became biochemistry on Earth. And we have some idea, that if you get gradients of temperature and acid and alkaline, the conditions that are naturally present on the surface of oceans, then complex carbon chemistry spontaneously happens. So we know that life, almost certainly we know that life began on Earth. And the other ideas that came from space or something like that probably began on Earth. So that means that at least here, that happened. And that we know that the conditions that led to the origin of life on Earth were present on Mars 3.8, 4 billion years ago. And we know that they're present on Europa's surface. So I don't see that there's anything special. Life is just chemistry. The idea that geochemistry becomes biochemistry is not fanciful because it happened here. So I think that given the same conditions, it would be surprising to me if the same thing didn't in that life begins. To test that is one of the great frontiers of science now. It's one of the great challenges, which is why another reason we're interested in Mars, because we know those conditions were there. We know there are what's called hydrothermal vent systems on the floors of oceans on Mars 3.8 or 4 billion years ago. So it would be good to know what I've said is right. And the way we find out is to find life or evidence of past life. There's a theory called the grand tech theory. So it's very hard to explain the evolution of our solar system. When you do computer models of solar systems, you don't tend to get 4 rocket planets close to the sun and 4 big gas giants further out. And one of the current best theories, and I say this because it shows you how lucky we might be, is that Jupiter, they tend to form these big gas giants and migrate inwards towards the star. So in almost all the computer simulations, just because you've got this big gas giant orbiting all the dust around the star, they tend to drop inwards. And it looks like Jupiter did that. So it looks like it formed and came in and came in almost to where Mars orbits today, and then cleared out the region around Mars, actually, which is maybe the reason Mars is so small compared to the other Venus and Earth. But then Saturn was coming in as well. And in the computer models, the interaction between Jupiter and Saturn stopped Jupiter coming in before it gets to the Earth. And they both get dragged out again, and so to where they are today. And so that seems to be, it's one of the best theories for the evolution of our solar system. So what are the chances? The chances of that are so minuscule, tiny. So that's the thing, I think, about these rocky planets. In order to get a civilization on Earth, I think you need quite unusual solar systems. And that would be a guess. And you need quite unusual stability on the planet for billions of years. And that's why I think we might be quite lucky. An answer would be, we are small, finite beings, right, which are just clusters of atoms. As we said before, they're very rare, but we understand roughly how they came to be. And we have a limited amount of time, not actually unfortunately, but because of the laws of nature. And the laws of nature forbid us to be immortal. Immortality is ruled out by the laws of physics. But also, what's interesting about if you look at the basic physics of the universe, from the Big Bang to where we are today, then the physics is driven by the fact that the universe began in an extremely ordered state. It was a very highly ordered system, and it is tending towards a more disordered system. And that's called the second law of thermodynamics. And what we strongly suspect, and I would say no, is that in that process of going from order to disorder, complexity emerges naturally for a brief period of time. So it's a natural part of the evolution of the universe that you get a period in time when there was complexity in the universe. So stars and planets and galaxies and life and civilizations. But they exist because the universe is decaying, not in spite of the fact the universe is decaying. So our existence in that sort of picture is necessarily finite and necessarily time-limited. And it is a remarkable thing that complexity has got so far that there are things in the universe that can think and feel and explore. And I think that is the answer. If you want an answer to the meaning of it all, is that you are part of the universe because of the way the laws of nature work. You are allowed to exist, or you're allowed to exist for a temporary, for a small amount of time, in a possibly infinite universe. What more do you want? When I see people who go, I want more than that. I want, there must be more to it. What do you need? The ingredients in our bodies were assembled in the hearts of long dead stars over billions of years, and have assembled themselves spontaneously into temporary structures that can think and feel and explore. And then those structures will decay away again at some point, and in the very far future there will be no structures left. So there we are, we exist in this little window where we observe this magnificent universe.
Modern science says the sun is the past, the earth is the present, the moon is the future. From an incandescent mass we have originated, and into a frozen mass we shall turn. Merciless is the law of nature, and rapidly and irresistibly we are drawn to our doom. Nikola Tesla. I'm Mike from This 25, and here are 25 space facts that will both terrify and amaze you. 25. The speed of light. Everybody loves to imagine themselves flying through the galaxy at the speed of light, at roughly 299,792,458 meters per second. However, the reality might be less fun and a lot more fatal. When coming into contact with an object moving at light speed, hydrogen atoms transform into intensely radioactive particles that could easily wipe out the crew of a starship and destroy electronics in seconds. Just a few stray wisps of hydrogen gas floating through the cosmos can have a radioactive output equivalent to a proton beam created by the Large Hadron Collider. 24. The Moon. Every year, our moon gets about 4 centimeters farther away from the Earth, and while this might not seem like much at first, it could have devastating effects on our planet in the future. Although the Earth's gravitational field should be enough to keep the moon from spiraling into space for good, the increasing distance between it and Earth will eventually slow our planet's rotation down to the point where a single day will take longer than a month, and our ocean's tides are locked in place.
23.
Black holes. Typically formed out of the death of massive stars, black holes are super dense regions of space with so much gravitational pull that they trap light and warp time. Just a small black hole in our solar system will throw planets out of orbit and tear our sun to pieces. If that wasn't scary enough on its own, black holes can hurtle across the galaxy at several million miles per second, leaving trails of destruction in their wake.
22.
Gamma rays. The most powerful type of explosion in the universe, gamma ray bursts are intense, high-frequency bursts of electromagnetic radiation that carry as much energy in milliseconds as our sun will give off in its entire lifespan. If one of these rays were to hit Earth, it could strip the atmosphere of ozone in seconds, and some scientists even attribute a mass extinction 440 million years ago to gamma ray bursts hitting Earth.
21.
Zero gravity. Scientifically referred to as microgravity, this condition occurs when an object is in a state of freefall and appears weightless. Although it may look like fun to float around like astronauts, prolonged time in zero-gravity conditions can have long-term mental and physical effects on humans.
20.
Cold welding. Here on Earth, gases in the atmosphere react with metals to create a thin layer of oxidization. The vacuum of space, however, has no atmosphere, and therefore causes no oxidation to form on metals, leading to an interesting reaction. This reaction is called cold welding, and it occurs when two metals of the same molecular makeup are pressed together and fused together permanently as if they were one piece. While this may sound neat, it caused quite a few problems on the first satellites and can make in-space repairs very tricky.
19.
Alien life. The universe is massive and unbelievably old, so the chances of other planets similar to Earth evolving life is not unlikely at all. According to Fermi's paradox, the high probability of extraterrestrial life out in space is contradictory to the lack of apparent evidence supporting it. At this point, we aren't sure which is scarier, the fact that we might not be alone in the universe, or the possibility that we are.
18.
Rogue planets. Launched into space after the formation of their planetary system, rogue planets are planetary bodies that are free to roam the cosmos, crashing into things as they go. Because they do not orbit a sun, rogue planets often have freezing surface temperatures. However, due to their molten cores and icy insulation, some scientists theorize that these free-roaming planets could contain massive subterranean oceans that support life.
17.
Travel times. In 1969, it took the Apollo 11 lunar module 3 days to land on our own natural satellite, the Moon. Since then, our technology has increased rapidly. We could expect to reach Mars in 7 to 9 months, and reaching Pluto would only take about 10 years. Distances outside of our solar system become even more extreme. Even traveling at the speed of light, it would take us over 4 years to reach the nearest star, Alpha Centauri, and over 100,000 years to reach the galactic center of the Milky Way.
16.
Extreme temperatures. Depending on where you are in space, chances are you're going to find yourself in some pretty extreme conditions. The heat put off by a supernova can reach temperatures of 50 million degrees Celsius or more, 5 times that of a nuclear explosion. On the opposite end of the spectrum, the cosmic background temperature of space measures minus 270 degrees Celsius, just slightly warmer than absolute zero. You definitely won't want to forget your jacket.
15.
The darkness. Being scared of the dark isn't just a silly thing that children experience. It's an evolutionary trait humans develop to protect themselves from dangers lurking in the unknown. The only reason adults nowadays don't fear what they can't see is because they have learned through experience that the likelihood of monsters hiding under the bed is very low. In space, however, darkness represents a completely unexplored emptiness that continues for an infinity. so being afraid of the dangers that lurk beyond our sights is a completely understandable reaction.
14.
Magnetars. Magnetars are incredibly dense neutron stars. In fact, they are basically an entire star crushed into a sphere only 15 miles across. 1 teaspoon worth of the magnetar contains the same mass as 900 Great Pyramids of Giza. They are also the hosts of the strongest magnetic fields in the known universe. Fields so strong that anything that gets too close is ripped apart at the atomic level.
13.
Musculoskeletal atrophy. Maintaining a healthy level of exercise is hard enough here on Earth, but in the zero-gravity conditions of space, it can be even harder. Astronauts visiting the International Space Station have exhibited signs of significant muscle atrophy after only 6 weeks in space, and that's with a rigorous health and fitness program.
12.
Venus. Despite getting its name from the Roman goddess of love, Venus is perhaps the most hellish planet in our solar system. With surface temperatures of nearly 500 degrees Celsius, atmospheric pressure 90 times that of Earth, and constant sulfuric acid rain, simply landing on Venus would kill you in moments. This definitely isn't a planet you'd want to have a picnic on.
11.
Dark matter/dark energy. We know very little about our universe. In fact, we've only seen less than 5% of the stuff that it's made of. The other 95% is dark matter and dark energy. About 1/4 of the universe is made up of dark matter, mass that we can't see or find in space, but must be there due to its effects on the behavior of its surroundings. The rest of the universe is dark energy, the true nature of which is mostly unknown. However, we are pretty sure that it plays a crucial role in the expansion of the universe.
10.
Background radiation. The Earth's atmosphere and magnetic field protects us from some really nasty stuff, namely radiation. Cosmic rays, solar winds, and electromagnetic particles permeate the universe, so much so that astronauts traveling between Earth and Mars will receive a full-body CT scan's worth of radiation every 5 to 6 days. Any that didn't succumb to radiation sickness before reaching their target would almost certainly develop severe cancer in their lifetime.
9.
The expanding sun. Our sun is constantly using nuclear fusion to combine hydrogen and helium together in order to keep itself burning. However, its hydrogen is not infinite, and as it gets used up, the sun will get hotter and hotter. Eventually, it'll get so hot that the Earth's atmosphere will be burned away, and our oceans will boil and evaporate completely. Then, once all the sun's hydrogen is gone, it will expand outward into a red giant, consuming the Earth once and for all.
8.
Hypernovae. With 100 times more energy than a standard supernova, hypernovae are powerful explosions that occur upon the death of a massive star. Although the factors that cause a star to go hypernova are widely disputed, we do know that the result is often a black hole or neutron star. Hypernovae are also the source of gamma ray bursts in the universe. They are bright enough to be seen by telescopes millions of light years away.
7.
Electromagnetic vibrations. Space is practically a perfect vacuum, meaning that you can count on the fact that your ears won't be picking up any sound while you're outside your shuttle. While the thought of complete silence might be maddening on its own, don't believe that just because you can't hear anything, that there isn't any sound. Due to the lack of gases for them to travel through, sound waves are not present out in space, but sounds are still transmitted in space via electromagnetic vibrations. NASA recorded some of these vibrations from select celestial bodies in our solar system and played them back, resulting in some truly chilling sci-fi horror effects.
6.
Everything can kill you. In space, there is no room for error. Even the smallest mistake can and will kill you. Out of the 430 humans we have sent to space, 18 never made it home. Advancements in technology have made space flights today much safer than they used to be. In the 1970s, nearly 30% of people who went to space died. However, the furthest we have traveled is our moon. A trip to Mars would increase the risk tenfold, and going beyond is still far beyond our capabilities.
5.
Time dilation. Imagine an astronaut traveling through space at speeds near that of light. Now imagine a person standing on Earth. According to Einstein's theory of special relativity, the astronaut will experience time much slower than the stationary person, although neither will perceive any difference in the time passing around them. When the astronaut finally returns home, even if it's been many years on Earth since he left, he will have only aged a fraction of that time. This is known as time dilation, and although we have yet to develop technology that allows us to move humans at speeds fast enough to notice its effects, we have seen instances of it while studying high-speed particles in a laboratory. 4. Hypervelocity stars. Thought to be the result of a close encounter with a black hole, hypervelocity stars are stars that have been ejected from their systems and sent rocketing through intergalactic space at speeds up to 2 million miles per hour. Although most of the hypervelocity stars we've identified so far are of similar size and mass as the Sun, they can theoretically be of any size and reach even more incredible speeds. 3. Solar flares. Despite the occasional sunburn, our sun has provided us with warmth and light for billions of years. However, don't let our local star fool you. Our sun is a vast miasma of incandescent plasma that can shoot out massive bursts of solar radiation at random. Although they are unlikely to directly endanger any of the life on Earth, these solar flares can create electromagnetic pulses that wipe out power grids, interfere with radio communications, and render technology invalid.
2.
Depressurization. There is no air in space, obviously. However, that implies more danger than just having to hold your breath for a long time. The human body is adapted to the atmospheric pressure on Earth, which is why when you go up in an airplane or travel over mountain roads, you might experience a popping in your ears. In the vacuum of space, there is no air pressure. Within moments of stepping outside your spaceship, all of the water in your body would boil and evaporate, expanding rapidly until you pop like an overfilled balloon.
1.
Big crunch / big rip. Everything must come to an end. But will there be an end to everything? Scientists agree that there will most likely be a permanent end to the universe, but how it will happen is still uncertain. One prevailing theory states that there will be a big crunch, in which the gravitational forces of the universe will reach their limit and cause the entire universe to cease expanding and fold back in on itself, eventually converging into a single infinitely tiny point before disappearing into nothingness. Another theory, known as the Big Rip, states that the universe will expand to the point that gravity loses all meaning, and the cosmos literally falls apart, even the particles and atoms eventually floating away from each other. I honestly can't decide which is more terrifying.